Hello and welcome to the Walking Talking Topic Multi-Mark Week 2 Question 2 with me, Mr. Barton. Now something a bit different for our multi-mark in this question, because instead of getting our usual one about costs and area and all that kind of stuff, we've actually got a lovely but very challenging question on sequences. And what I like about this is it eases you in, a bit of a false sense of security here with two nice simple nth term questions to start with. So write down the nth term of the following sequence. So this sequence here goes 6, 13, 20, 27. I reckon, if my maths is right, that sequence seems to go up by 7 each time. So I think that's something to do with the 7 times table, or 7n. And I tend to write the 7 times table just above, so 7, 14, 21, 28. And I ask myself, what do I do to get from the 7 times table to my sequence? Well, it's the 7 times table with 1 taken off each time. So 7n take 1 for that one. This particular sequence seems to have a difference of 6, and it seems to be going down each time. So I know that this is going to be something to do with my 6 times table. Because it's going down, it's my minus 6 times table, my minus 6n. I'm just going to write my minus 6 times table above it. So I've got minus 6, minus 12, minus 18, minus 24. And I'm going to ask myself, what do I need to do to get from a minus 6 times table up to this number here? Well, to get from minus 6 up to 26, I've got to add 6 on to get to 0, and then another 26 on to get to 26. So I think I've got to add 32 on. But I'm a bit dodgy at them sometimes, so I'm just going to double check. Let's say to get from this last one, minus 24 up to 8. Well, to get from minus 24 to 0, I've got to add on 24. And then to get up to 8, I've got to add on another 8. And 24 add 8 is 32. So that's looking good. If you want, you can write that as 32 take away 6n. Who cares? You're helping yourself to 4 marks. So you're feeling good about yourself, thinking, oh, this isn't too bad, this question. And then this comes along. The diagram shows some tile patterns. Each pattern has some shaded tiles and some white tiles. And there's pattern 1, pattern 2, and pattern 3. Find an expression for the total number of tiles in pattern N, the expression for the number of shaded tiles, and the expression for the number of white tiles. Now I'm going to show you how I approach this question, and this might be different from how you approach it, but I'm just going to approach it in a kind of diagrammatical, hopefully fairly logical kind of way. But there are lots of other ways of doing this. And I should say one way that you can do this is just work on pure numbers if you want. But to do that, you've got to know your rules for finding nth terms of quadratic sequences, which are a little bit tricky. But by all means, if you want to practice that, and you'll find loads of videos on the internet, try that. But I'm going to show you how to do it a geometric way, using just the pictures themselves. Okay, so I'm going to start by probably the hardest bit actually, which is the total number of tiles. Now I've got a square here in pattern 1, and it's got a base of 2 and a height of 2. Now in pattern 2, I've got a square that's got a base of 4 and a height of 4. And in pattern 3, I've got a square that's got a base of 6 and a height of 6. And if I was to imagine pattern 4, let's think about pattern number 4, I reckon that would probably have a base of 8 and a height of 8. So what about pattern N? What would the base of pattern N be? Well, the link seems to be whatever the pattern number is, if you double it, you get the base. And because it's a square, you're going to get the height. So if I draw my square for pattern N, I think it'll probably have a base of 2 lots of n and a height of 2 lots of n. Now all you're left to do then is work out, well, what's the area? How many squares inside? Well, there's 4 squares inside there, 2 lots of 2, 4. Here there are 16 squares, 4 lots of 4. Here there are 36 squares, 6 lots of 6. So in pattern number N, so I'm going to call this here the total squares, it's just going to be 2 lots of n times 2 lots of n, which so long as you're good at your algebra, I think is 4 lots of n squared. So that's how we get the total number of squares. Now let's have a think about the shaded squares. And again, I'm going to take a diagrammatical approach to see what I've got here. Now it's probably easiest to spot on pattern 3, to be honest with you. Can you see on pattern 3 here, you've got a 3 by 3 square there. Let me just highlight that. You've got a 3 by 3 square, and then you've got another 3 by 3 square. And on pattern 2, you've got a 2 by 2 square, and you've got another 2 by 2 square. And on pattern 1 it looks a bit dodgy, but look, the pattern continues. You've got a 1 by 1 square, and you've got a 1 by 1 square. So you've got 2 lots of the pattern number squared. Can you see that? Because here you've got a 3 squared and a 3 squared. And here you've got a 2 squared and you've got a 2 squared. And there you've got a 1 squared and a 1 squared. So on your nth term, you're going to have down here an n squared, and up here you're going to have an n squared as well. N squared and n squared. But then we've got this little thing. But that's okay, because these just common to every single one of these patterns. So your shaded ones, you can have 2 lots of n squared, 2 lots of your pattern number squared, and then you're going to have your little extra one, which is common to each of your patterns. So it's 2 lots of n squared plus that one common shaded square. Now what about your unshaded squares? What's going on here, and can we do something similar? Well, it turns out we can. And again, if we look at pattern 3, it's not too bad. Look at that. We've got a 3 by 3 square there, and we've almost got a 3 by 3 square at the top, apart from this little annoying shaded one there. And it's similar here. Look, we've got a 2 by 2 square, and then we've almost got a 2 by 2 square, but we've got this annoying little shaded square there. And here it's a little harder to picture, but you've got a 1 by 1 square, and you've almost got a 1 by 1 square, but this shaded one's in the way. So each time, one shaded square is stopping us getting 2 lots of our squares again. So again, we've almost got 2 lots of our pattern number squared, but this time, instead of having an extra one, we've actually got 1 too few. So the total number of unshaded squares is 2 lots of n squared take 1. Now let me tell you the beauty of this. You can check. Because your total number of shaded squares plus your total number of unshaded squares should equal your total number of squares. It works in numbers. Like if we take this one, we've got 4, 8, 9 shaded squares, and we've got 10, 11, 12, 13, 14, 15, 16 unshaded, which is going to give us the 16 total squares for that. But we can check it with algebra. Our total number of shaded squares is 2n squared plus 1, and our total number of unshaded squares is 2n squared take 1, and if we add them together, we get 2n squared plus 2n squared, which is going to give us 4n squared, and we get a 1 take a 1, which disappears to leave us with 4n squared, which is exactly what we hoped it would be. So there are your answers to what I thought, but I'm a big maths geek, was a lovely question.